In this talk, we're going to talk about two basic ideas. One is called Flynns Taxonomy, which is a way of kind of categorizing different parallel architectures. And then we'll also take a look at some basic performance metrics for measuring how efficiently parallel computers are operating. Flynns Taxonomy is a time-honored way of kind of categorizing the architectures of parallel and distributed machines. And it kind of splits things into two different dimensions: the instructions that are being executed and then the data that are being processed. From the instruction point of view, we can have either a single instruction operating at a time or multiple instructions operating simultaneously. The idea here is that in some architectures you have just a single stream of instructions that are being applied to every piece of data that's currently in view in the algorithm. And that's in contrast to multiple streams of instructions that are all executing simultaneously and can do different things at the same time. On the other side, we have the different types of data, and that's also categorized in the same way. We can think about operating on a single datum or a single stream of data at a time, or on multiple streams of data simultaneously. And the combination of these two things, the data and the instructions, either single or multiple, give rise to these four categories, which is really the meat of Flynns taxonomy. So we can have, and these have goofy pronunciations, we can have SISD, which is a single instruction, single stream of data, MISD, which is multiple instructions on a single stream of data, SIMD, which is single instructions on multiple data, and MIMD, multiple instructions streams running on multiple sets of data. So I want to kind of unpack these four things a little bit. So first, a SISD is really just the idea of a traditional single processor. In that we can't really hardly buy a single CPU anymore. You can buy a chip, but it's going to have multiple cores on it, so it's sort of inherently a parallel machine. But if we think about just like a single core of a modern processor, that really qualifies as a SISD architecture. So it's not really a parallel computer. It's sort of the minimalistic base case here when we're thinking about Flynns taxonomy. So for a very long period of time, as we talked about when we were looking at the evolution of processor architectures, for a very long period of time, all we had really were SISD processors, at least in the microprocessor space. So it's a simple sequential machine. There's one stream of instructions running on one stream of data. So if you just kind of think back to ICS or computer architecture, you've got one program counter that's bringing instructions in from memory. It's executing one of those instructions at a time, at least conceptually, and you're operating pretty much on a single data set. You might be iterating over an array or a linked list or something like that, but the fundamental behavior of the machine is going to be one instruction running on one collection of data or one stream of data at the same time. The second category here in Flynns taxonomy is SIMD. In this case, we have a single instruction, but we're operating on multiple pieces of data simultaneously. And this is actually a very common way of categorizing the way that GPUs behave. So in a GPU, you might actually have one processor or one control circuit that's orchestrating the behavior of a bunch of different processors, but each of those processors are basically doing the same instruction at the same time. The parallelism arises because each of those processors is accessing a different portion of the data set. So if you've got a rendering engine that's trying to draw graphics in real time, you might be doing the same operations orchestrated by the same kind of control circuit, but each of the processors that are participating in that calculation are going to be operating on different pixels or different scan lines or however you partition the data. They're doing the same thing, but with different inputs and therefore generating different outputs. So SIMD, very, very common kind of architecture in the GPU space. Let me skip to MIMD. So MIMD is multiple streams of instructions operating on multiple streams of data. So similar kind of an idea to SIMD in that we can focus on multiple portions of our data set simultaneously. So again, if we think about like an image processing application, we might be working on different pixels or different voxels or different scan lines or whatever. Or in say a matrix operation, different rows of the matrix on different processors. What's different between MIMD and SIMD, though, is that in the SIMD case, all of those processors that are operating on those multiple data streams are basically executing the same instructions at the same time. So they're all going to add at once, they're all going to move at once, they're all going to do whatever. Whereas in the MIMD case, you can have completely separate programs that are running on each of the processors. So in principle, you could have a completely different program running on every one of the processors, each of which was doing a different thing to different parts of the data set. So in that sense, the MIMD architecture is sort of the most flexible, but also the most complex. And a good common example of a MIMD machine would just be a typical multi-core CPU. Although if we only think about one core at a time, we're sort of back in the SISD realm. In reality, we have multi-core CPUs, and each of the cores in those multi-core CPUs is itself a full-on processor, right, with caching and a control circuitry and branching and branch prediction and all that kind of stuff going on in each of the cores. So a multi-core CPU can execute programs that are written using this MIMD model because each of the processors can do its own thing independently of the other processors, as opposed to SIMD, where every processor has to do the same thing at the same time. Okay, and then the fourth category here that I kind of skipped over is quite rare. It's multiple instruction, single data. So you're getting parallelism because you have multiple instructions that are being executed simultaneously, but they're all kind of operating on the same data set, which, if you step back and think about it, that doesn't really make a ton of sense or along the lines of increasing performance, but it can be used to increase reliability. So in machines that are designed to be fault tolerant, this would be an approach to designing that architecture, where if you had several processors that were doing the same calculation, you could architect it in such a way that you'd have multiple threads of control doing the calculation. And if you wanted to verify that there was a high likelihood that the calculation was being done properly or consistently, you could compare the results of those calculations. And if they matched, you have a fairly high confidence that the system is working properly. And if one of those calculations or one of those processors should fail, for example, the other processors that were also doing the same calculations could just continue going and take over for the failed processor. So this idea of a fault-tolerant computer follows that kind of an architecture. Even if the processor itself or one of the processors completely goes haywire, if it stops agreeing with the other processors, the hardware and the operating system on that type of a machine can actually dynamically swap out that processor, and if allowing the system administrators to put in completely new hardware without ever turning the machine off. So also a very important kind of application for, if you're running a stock market or something like that, you just don't want that thing to go haywire, to go down in the face of some sort of a hardware failure. So that MISD architecture does show up in that context. In this course, we're going to focus principally on SIMD and MIMD, and as I've indicated here, right, that basically corresponds to doing GPU stuff and doing multi-core CPU stuff. Let's drill down into the MIMD category here a little bit more. So I've simplified the Flynns Taxonomy here to just show the basic architectures, and I want to look at the multiple instruction, multiple data architecture. And we'll see that we can kind of split this into two very distinct types of architectures that are called shared memory and distributed memory. And then within the distributed memory, there's a further division. Here's a very simple picture of that first case, the shared memory MIMD machine. The idea here is that all of the CPUs have access to the same shared memory. They're all going to have the same data set available to them. They might not access the same elements in that memory at the same time, but the hardware is such that they could if they wanted to. So here's a little illustration of that, of seven cores, the C0 through C7, and they're all directly connected to a single M sub-shared here. And this is essentially the default architecture for most common microprocessors, right? If you have an 8-core Intel Core something processor, each of the cores, although they're independent processors, which is where we get the MI from, they're independent processors. They have access to the same memory space. They've got different caches that are unique to them. The level 1 and level 2 caches are independent of one another. The level 3 cache is usually shared, but ultimately the truth, the state of the computation is that caching mechanism is transparent to the processors, and everybody eventually is going to hit main memory. And it's the same main memory that is accessible from all of the other processors. An advantage of this approach is it's relatively simple, right? Well, simple is a relative term here. It's quite complicated to actually implement that in practice. But conceptually, it's a fairly simple model. Some problems with that. One is that everybody has access to shared memory, right? So if you, depending on the memory protection and what the operating system is doing and that sort of stuff, you may end up with issues with overwriting one another in shared memory, or if you have a thread model where everybody's running inside the same process, you've got to worry about things like one processor reading from a location at the same time that a different processor is writing to that same location, because now you're going to have an unclear result. Did you read before the write or after the write? The other issue here is that this architecture becomes kind of a bottleneck to scalability. By scalability, we mean, in this case, growing the number of CPUs that we can throw at a problem. Because the CPUs each have to be connected to the same memory subsystem, the complexity of the circuits to interconnect the CPUs to the memory kind of start to dominate the architecture, and at some point in the small number of maybe dozens of processors, you reach the point where it's no longer worth it to add more CPUs that can all talk to the same memory system. On the other hand, again referring back to this diagram, where we have the shared memory possibility that we just described, and then the other alternative is a distributed memory system. So here we have a single memory with a bunch of processors. Here we have a bunch of memories with a bunch of processors. So in the distributed memory case, we're going to have a memory subsystem associated with each of the cores in the processor. Now you can add additional processors to the picture. As long as you add additional memory units, you can kind of scale this arbitrarily largely, because each of the CPUs has its own local memory. A simple example of this kind of architecture would be a network of workstations. So in the lab, we've got a bunch of different computers, each of which has processors and memory that's exclusively accessible to those processors, and then they're interconnected with one another over a network. And that's what I'm trying to indicate here at the bottom of the picture. That's some sort of a network. I'm showing a simple kind of bus network here where all of the CPU memory combinations are connected to the same physical network, and this would be an example of, or rather the Ethernet would be an example of this. So each CPU has its own local memory. Each of the individual CPUs can really do anything, right? It's a simplifying assumption that's often made in this type of architecture, that you have sort of identical machines that are all collaborating together, although they don't have to be identical. But we get the MIMD nature of this, we get the MI part, the multiple instructions, because we've got a bunch of independent CPUs. And the memory access is not a bottleneck any longer within a single CPU memory combination. However, we also introduce some additional complexity in that we've got to now figure out how we communicate between CPUs over the network, which means that instead of just being able to access memory directly, as was the case when we had each of the CPUs connected to the same physical memory, now we have to be able to communicate back and forth between CPUs. So again, in that network of workstations example, one processor on one machine can't directly access the memory on another machine. They have to agree somehow to communicate information back and forth to each other in order for them to share data as the problem is solved. There's the kind of two, again back to this picture, there's sort of two ways of architecting software in the distributed memory case. One is this idea of a symmetric algorithm where each CPU is pretty much doing the same kinds of calculations. There's no kind of one processor that's in charge of everything else, which can become a bottleneck. The other approach is called the master-worker paradigm, which is in that case you will have a designated processor that's kind of in charge of the calculation, and its job is to sort of orchestrate the behavior of the other processors in the multi-computer to do their portion of the calculation, and then that master processor kind of brings all those intermediate solutions together to come up with the final answer. This is often the case for a GPU-based system, where we'll see that most of the time the GPU itself is going to be kind of a worker bee, and it's going to be controlled and the behavior orchestrated by a core on the CPU itself. There's a couple of other architectural models that have arisen since Flynn did his original work. One of these is called single instruction multiple thread. And this is a kind of a variation of the SIMD, single instruction multiple data. It's really terminology that came from NVIDIA, right? The CUDA people, where they organize the computation on their GPUs into something called threads, and they actually have a quite specific meaning for that terminology. But it basically, you have a single set of instructions that are running on all of the GPUs that are participating in a calculation, but not all the CPUs need to be active at the same time, and because it's a multiple thread or multiple data thing, they're all operating on different portions of the problem. So it's a little bit higher level abstraction than the traditional SIMD architecture, but suits the kind of the hardware model that NVIDIA has for their GPUs. So it also offers a relatively simple programming model, although when you have threads that are going to do different things on different data, it tends to reduce performance, right? Because one of the things that a thread can choose to do is just basically to do nothing during some portion of the calculation. And whenever you have a piece of hardware in a parallel computer that's not doing anything, you're going to lose performance, obviously. So we'll unpack that single instruction multiple thread model in a lot more detail in the GPU portion of the course. And the other common model, and this is kind of a variant. So I said that this SIMT is a variation on the single instruction multiple data architecture. SPMD, or what's usually called SPAMD, is a simplification of the MIMD architecture. So in MIMD, strictly speaking, we could have, if we have 100 processors, we could be running 100 different programs, and that would fit into the multiple instruction part of the taxonomy. In practice, that's pretty rare. You're going to normally run a single program on all of the processors in the machine. They might be running different parts of that same program, but at a little higher level of abstraction, they're all basically doing the same thing in the sense that they're running the same code. So when we say single program multiple data, that's what we mean. And that's really the model that we're going to adopt when we start looking at implementing these things. There's one program, but each of those programs is operating on an independent processor. So although they're running the same code, they don't have to run the same instructions from the same code at the same time, which would be the case for a SIMD model. But because they're running the same program, it's not really as general purpose as true MIMD. So each processor runs the same program, not the same thread, so we have independent execution and control. And again, that's really the paradigm that we'll use in practice when we start doing threading and distributed computing. Let's consider some performance metrics that we want to use when we're measuring the behavior of our different algorithms and trying to understand how things scale and so forth. These are the two most common metrics for evaluating the performance of different parallel algorithms. There's some nuance to it, and that we'll unpack as we go, but these are kind of the key ideas. So the first metric for evaluating a parallel computer is called speed up. The idea here is that if you're going to have P processors working on a problem, what you want to do in order to understand what kind of bang you're getting for your buck is compare the performance of those P processors against a single processor. And the fundamental unit here really is runtime. I guess I should add that as a separate element here in the talk. But we want to measure the amount of time it takes for the problem to be solved. And we'll look at some ways of measuring that and what to include and what not to include and so forth as we go. But at least conceptually, you might just think of this as kind of the wall clock time, right? From the time you push the go button until the time the calculation is completed and stored on disk or printed on the page or wherever, that would be the runtime. And obviously, intuitively, if you run a program on one processor, it's going to take some amount of time. And if you run it on more than one processor, you hope, I mean, that's just kind of the point, you hope that it's going to go faster. But the question is, how much faster is it going to go? And that's kind of what speed up gets to. So if we have these two runtimes, so T sub 1 would be the runtime on one processor, and T sub P, the runtime on P processors, the speed up is just given by this really simple equation, T sub 1 divided by T sub P. And just intuitively, if the P processor performance is better than the one processor performance, then T sub P is going to be shorter. It's going to take less time to run on P processors, and that ratio is going to give us the speed up. Here's just some remarks about speed up. First of all, speed up is normally going to be in a range from 1 to P. If I put P processors on the problem and they don't go any faster than one processor, I get a speed up of 1 because that ratio has the same numerator and denominator. It's not really a speed up at that point, I guess. On the other hand, if I can put P processors on a problem and each of them does 1 divided by P of the work and there's no overhead or any loss of efficiency, I'm going to go P times as fast, so my speed up is going to be P. We have a particular name for that. When S is equal to P, it's called linear speed up. And I've noted here that that is really rare. There's very few cases in a real-world problem where you're going to see linear speed up. It's kind of a game of diminishing returns. You add more processors to the problem, and it's not necessarily clear that there's going to be this nice, easy relationship between adding processors and getting faster. So it is rare. It is possible, and there are what are known as embarrassingly parallel problems, where it's really easy to partition the problem into individual pieces, and those kinds of problems generally do yield a speed up that is essentially linear, but those don't happen very often in practice. And a lot of what we'll do in this semester is going to orbit around figuring out how to increase the performance and the speed up. By recognizing some of the challenges that come into play when we're trying to get good speed ups and figuring out how to ameliorate those things. As I mentioned, we're going to measure the performance in wall clock time, and there's some subtleties to that. It's hard to measure. It's also influenced by a whole variety of other kind of non-objective factors. Did you have a good implementation of the algorithm? Did you choose the right algorithm? What did the compiler do? What were the optimization settings on the compiler? How does the operating system schedule jobs on multiple processors? What other things are going on the computer at the same time? Right. So there's a lot of variability in some cases to measuring these things, and that's just kind of part of the nature of empirical computer science, right? We're gonna have to be aware of these things. We're gonna figure out ways to try to reduce their impact, and then we're also going to just do some sort of obvious things like run an experiment multiple times and take an average value for some of these timings before we do our calculations of speed up. Ideally, we'd like to have the tests run on identical hardware and software and under identical conditions. So ideally, you'd want to have no other jobs running on the computer, or if you've got a distributed system on the computers that make up, say, your network of workstations. And then we also want to use the fastest sequential algorithm that's available. So we don't want to kind of cheat with our results by using a sequential algorithm that has a worse time complexity or space complexity in big O terms than what we're using for our parallel algorithm, because it will sort of artificially inflate or artificially deflate, if we go the other direction, our performance numbers. So again, a lot of these things are kind of subtle, and we'll unpack them as we go. But the key result here is that we're going to measure our runtime on one processor, on more than one processor, often in powers of 2 as we go. And then we're going to calculate, given a variety of experiments that give us an average runtime, we're going to use that to calculate our speed up as a measure of how well we're doing in terms of making the problem solve more quickly. Closely related to speed up is the idea of efficiency. So where speed up just tells us how much quicker we're going to be able to solve the problem, efficiency tries to get at how well we're making use of the underlying resources in our multi-computer. It's defined, again, quite simply as the speed up divided by p. And if you unpack that, that's t sub 1 over p times t sub p, where p is the number of processors. Again, a simple calculation, easy to make once we have gathered some timing data, and of course we need to keep track of the number of processors that we're using. Some remarks about this: whereas speed up ranges from 1 to p generally, efficiency is going to be in the range of 0 to 1. So if I have terrible efficiency, in other words, as I add more processors to the multi-computer, the denominator is going to grow, but if the speed up doesn't grow commensurately, my efficiency is going to tank, right? It's going to be down close to 0 if I'm not making good use of those p processors to solve the problem rapidly. On the other hand, if I use all of those processors optimally, in other words, if I get linear speed up, we can see from back here, a linear speed up would basically mean that my efficiency is going to be 1, right? I'm going to be using all of those resources at their maximum, with their maximum speed ups, and that's going to mean that I'm using everything with maximal efficiency. Because its range of 0 to 1, it's sometimes expressed as a percentage. When I ask you to do analysis, I'll stick with the 0 to 1 range, but it's really common to talk about 80% efficiency. It really just means a big E of 0.8. As I mentioned already, linear speed up gives us P over P for the calculation, which is 1 or 100%. And because this is dependent on having linear speed up, the efficiency being 100% or being 1.0 is also quite rare. And this is kind of why that's the case. One of the things that we're trying to do when we're thinking about how to take a sequential algorithm and parallelize it is we would like it for the parallel algorithm to do no additional work than the sequential algorithm does. Right? If we're think about just like a simple sorting problem, there's no overhead other than moving the data around in memory and doing comparisons and calculations. Coming up with the midpoint in a sort. All those things are directly contributing to solving the problem on a sequential processor. On the other hand, when we bring more than one CPU into it, there's going to be additional work that the multi-computer is going to have to do that can just be thought of as overhead. It's things that don't contribute directly to solving the problem, but that are necessary in order for us to implement a parallel algorithm on multiple processors. So for example, in the case of a distributed memory architecture especially, where you have independent CPU and memory units that are talking to one another over a network, if they need to be able to share information between the subsets of data that are being processed on each CPU, there's going to have to be some communication. That wouldn't be necessary in a single processor sequential implementation of that same algorithm. So the fact that we have to do that communication means that there's going to be time spent doing something other than solving the problem. Or in the case of a shared memory architecture where you have all the CPUs that are connected to the same memory, Now you're gonna have contention over that memory. Not all of the CPUs are going to be able to access every element of memory at the same time, and even if the hardware is sufficient to allow that to happen, the algorithm itself might impose constraints on who can access what portions of memory at the same time. As I mentioned before, we end up with these race conditions where you get reads before writes or writes before reads in an unpredictable way that causes the algorithm to break. So in order to circumvent those problems, we have to do things like introduce intentional locking and other things that will prevent processors from sort of stepping on each other's toes in that shared memory. Another source for overhead is if we have an unbalanced workload. When we have just one processor, that one processor is busy the whole time running code that's directly associated with solving the problem. If we have multiple processors, and if those processors are not allocated a share of the work that needs to be done in an even fashion, you might have 5 processors that are really busy and 5 processors that are sitting around twiddling their thumbs a lot of the time, which means that you're going to leave processing power underutilized, and that's also going to reduce the overall speed up and therefore the efficiency. And you might think that if you're in that kind of a situation where you have some processes that are really busy and other processes that are sitting around idling, that, well, why can't we share some of the work between the busy processors and the idle processors? That's called work balancing or load balancing, and that's a legitimate solution to that kind of a problem. But take a step back again and realize that that is not something you have to do in the single processor case, in the sequential case. So load balancing itself is a source for overhead in a parallel algorithm. So having that unbalanced workload is itself bad, but doing the load balancing itself will also reduce your speed up and therefore your efficiency.